All right. So, if you remember where we left things, the last time we have introduced the Broglie wavelength. We have gone through the Bohr atom, we have introduced the Broglie wavelength, right? So, now, as a primer for what we will do, the focus is to actually do the real solution of the hydrogen atom today. But we need to know what we're gonna solve. So we need this little equation. So we're gonna do that first. This is the Schrödinger equation. Now we had the Broglie's wavelength, right? So we know that was the wave-particle duality, yeah? That also particles have wave-like character, like photons, like we have discussed many times during the course. We know, of course, that the energy of the photon now, hc divided by lambda, equals to h nu equals to h bar omega, where omega is our angular frequency. This we have seen many times. We also now introduced, of course, that the momentum of the photon, but now the particle also, the Broglie hypothesis. I'm going to put it just in the x direction. You can do this in 3 dimensions. It's straightforward. It's just a little bit symbolically different, right? So we're going to put it in the x directions, and then we knew that it was h divided by this, the Broglie wavelength, right? Which we can then, of course, write as h 2 pi divided by lambda, h bar k, where k is the wave number. Okay, so, well, then we're going to consider a plane wave again. But now for the particle. The plane wave, then, which I'm going to write as a function phi xt equals a ei kx minus omega t. Okay? Now, often, and we'll go through, you see this in your textbook as some phi, but I'm so bad in writing the symbols, so I'm just going to write it as phi. You see it as psi. Okay? That's just to make touch with standard notation. Okay, we're going to play around just a little bit with this first. We're going to take the time derivative. This is, again, just things that we have done. If we take the time derivative of this now, the phi, the t, we know that the wave-like character means that it basically just comes out, right? So in this case, this is just minus I omega, yeah, times the function itself. It's just a reflection of that, okay? And then we're going to multiply it by I times h bar. So we multiply this by I times h bar. We get the phi dt. And on this side then, well, we have omega h bar, right? And omega h bar is just E. Up there, the Broglie, right? So that's just E phi. So that's a little neat equation that we have. Can call it 1. So then we're going to play around a little more. We're going to take the spatial derivative. Well, that just works out the same, right? The phi dx is just going to be, now it's ik that comes out, okay? Let's do the same. Multiply it by I h bar. So that's I h bar, the phi dx. And on this side now, well, we get a minus sign. And then we have h bar k, right? But h bar k is just the momentum. So that's just minus px phi in this wave picture, all right? So we're going to take the second derivative as well, the 2 dx squared, partial derivative, yeah? And, okay, then we just have to take this one more time, and then, of course, another one comes out, so the 2 phi, the x squared, is just minus k squared phi. But minus k squared, we might just use this relation, right? So we can write this as px squared divided by h bar squared phi. Okay, we can call this 3, we can call this 2. So let's say now that our particle is free. Yeah, it's just freely moving out there. Then the total energy, which previously I called W, right? Now, I will follow the custom here and call it E. So that's just lovely now, because in the radiative transfer language, we have E as the energy density. In the electromagnetic description, we had E as the electric field, and now we have E as the total energy. It's nice being an astrophysicist sometimes. For a free particle, that's just the kinetic energy. Okay? The kinetic energy in this case, we're moving along the x direction, right? We can write as px squared divided by 2m. That's just your mv squared divided by 2 written in terms of the momentum. But using this now for the free particle, we see that we can combine these two. Number 1 we had over there, and number 3 we had over there, right? Because we have the energy, can write it in terms of the momentum, so we get this. I h bar the phi dt equals, instead of E now, px squared divided by 2m phi. However, for that we can use this one. So we see that we can write this as minus h bar squared 2m phi dx squared. So where did we end up? We ended up with the equation for the free particle, the wave equation. So this is the wave equation for the free particle now. Okay? Now, that was very straightforward and nice. So, and now we come to the postulate. We're going to suppose that these relations for the energy and the momentum that we put up for the free particle, we can see them as operators now, and they also hold for a non-free particle moving in a potential. Okay? That is, in a situation where the total energy is not just px squared divided by 2m, but px squared plus a potential. Now for us today, this potential is only going to be a function of essentially the radius. It's going to be the Coulomb force, right? And if we now do that, since we know that this was originally, right, we had this to be E phi, we can just, by going through this again, see that what we end up with is the phi dt equals minus h bar 2m plus u d2 dx squared plus u phi. And this is then the time dependent Schrödinger equation. Of course, we have not derived it. We have just made it appear plausible that we have this. You cannot really derive the Schrödinger equation like that, just like you cannot derive Newton's laws of classical physics. Newton's 3 laws of motion. So that's our time-dependent Schrödinger equation for you right there. So, like I said, if we now specify that this potential, which later today will be a function of r, that is the radial position, but we're going to take it now to be a function of x. It is not a function of time, right? Then we can suppose that we have a solution to the time-dependent Schrödinger equation that is on this form, which I will call now alpha of x times f of t. That is, that it is separable. We have one spatial component, we have another time component. Okay? Then we can take the partial derivative. Well, we know that we're going to have to deal with two partial derivatives in space, right? So we're going to do that. We're going to say that the 2 phi, then, we can just call this alpha f, yeah? The 2 phi, the x2, that's just going to be the 2 alpha, the x2 times f, because that's only a function of time, okay? Similarly, we can do it in time. The phi dt, right? So that's just going to be the f dt alpha. Okay. Let's insert that there to see where we're at. We're at I h bar. Instead of the phi dt, we're going to use this one. So we have alpha, the f dt. And then we're going to have this to be minus h bar divided by 2m. And then we're going to take the 2 phi, the x2, which is just that one. So that's the 2 alpha, the x2 times an f, right? And then we have the potential. So u times phi, which is just alpha f. We know, we can suppose from before that this is just the energy, right? Times phi, which we have supposed is alpha f. Okay? Now the interesting thing, of course, appears here that, well, let's take the time first, time part only. That part, and then use that. Then we see that we can get rid of the alpha, which is the spatial part, right? So we have an equation only depending on f. And that is then I h bar the f dt 1 over f equals to e. Okay. The second equation here, the space part, we see that we can get rid of the f, right? We divide through, we divide through, we divide through. So we get for the second, the space part, this is the time part, and this is the space part. And for the space part, we get h bar 2m the 2 alpha, the x2, and then we have divided by that, so we get u alpha equals to e alpha. Okay? The general technique that I'm using here, of course, when you learn this in your, probably in your mathematical methods in physics course or something similar, is called separation of variables. Yeah, so you can make that connection. And there are certain rules that you can learn in order to apply this technique then to also more difficult situations, of course. Just to make contact. Well, this one we see we can solve directly, right? This is a type of equation we have solved many times in this course. Remember we had like the I over I equals to something on the right-hand side. So this will just be an exponential. We already know that we can write this as then f equals some f0 e, and then we have e. We have an e divided by h bar divided by I, but it's custom to multiply this by I upstairs and I downstairs and then get a negative. So you get negative E divided by I h bar t. Okay. The space part here, we're going to replace alpha with our phi. I didn't have to write it so many times, but I did now. Then we get this here, the 2 phi, the x2 plus u phi equals to e phi. Often you see this as h phi equals to e phi, where h now is your Hamiltonian operator. And this is the one-dimensional time-independent Schrödinger equation. Okay. So we're going to take some help from the Grandmaster and solve this today for our hydrogen atom. In which case the potential will just be our E squared divided by R, right? So that's just the Coulomb potential for you again. Now the thing with the Coulomb potential is, of course, it depends only on the position R. So it's not time dependent. That is good. We can apply the separation of variable, get to this. Solve the time independent Schrödinger equation according to this. But since it's dependent on R, it's going to be more convenient for us to do this in spherical polar coordinates. Yeah? So here we did it one-dimensional in the x direction. But we know that when we go to three-dimensional, then of course this produces the Laplacian operator. X, Y, Z, this is trivial. In spherical polar coordinate, it's a mess to work it out, but it can be done. And that's what will be done. Now, the interpretation then of the solutions is that the E's that will come out will be the energy eigenstates of the hydrogen atom that we will solve. Now, the interpretation of this phi function here, the wave function, is that the amplitude squared, which normally is a complex amplitude, times in some volume, dV, is equal to the probability of finding the particle within that differential volume element V. So essentially, what we have gone from then, if we can find the solution, we can solve for the phi values. We have gone from Bohr's picture where we had the electron here in some fixed orbits, and then transitions between them, like we learned, yeah? And they were stable, to essentially an electron probability cloud. That is, we can only calculate the probability of the probability that the electron is within a certain volume element, or as we will see, within a certain radius, okay, at a certain radius. I forgot to mention one thing, of course. Since these are separable equations, yeah, you can also see that both of them has to be fulfilled, right? And the only way they can do that is that E is indeed a constant. And that's then why we call it the energy eigenstate in this case. All right, we're good. That was the Schrödinger equation.